Hello everyone, this is Maz with Tianadena. I would like to welcome you all to this session. Today we have a special presenter, Dr. Ben Deaton from SGH Boston office. He's going to talk about nonlinear finite element analysis of 3D reinforced concrete beam and column joints. But before we get started, I would like to give you some heads up. Your microphones will be muted during the presentation. This is just to avoid any background noise. And this session will be recorded. So after this webinar, if you need to have this session, please send me one email. Then I can send you the recorded link. Also, if you have any question, you can use the chat box. You can write your question and send it to us. Ben gonna check it. If it is general, can answer that through the microphone. If it is very specific, we can either type you back or we follow up the discussion by email. So I'm gonna hand over the session and panel to Ben. I'm gonna make you presenter, and I think you're good to go. Ben, can you hear me? Ben, I cannot hear your voice. Maybe there is something wrong with your...
Hi, can you hear me now?
Now it's much better. So
okay, great.
It's all yours. Good luck.
All right, thank you so much, Maz. I'd like to begin by thanking each of you for taking the time to attend the webinar today. I hope you'll find it interesting and informative, and it's a real pleasure to have the opportunity to do this. I'd like to begin today by introducing myself and giving a bit of context for my background. I recently completed a PhD at Georgia Tech in Atlanta, Georgia at the end of 2012. This was advised by Dr. Kenneth Will. My research there focused on nonlinear constitutive modeling of reinforced concrete, and this was my first exposure to Diana, and today's webinar will be based on that body of work. So I'm now working as an engineer at the Boston office of Simpson Gumpertz Heger, which I joined in early 2013. And I'm a member of the Engineering, Mechanics, and Infrastructure Division. And we provide a high-end consulting service in engineering mechanics to the building, nuclear, science, defense, wastewater, and transportation markets. And we are routinely working on challenging assignments like the ones I'll be discussing today. And we use the very best tools like Diana to get the job done. So that's a brief snapshot of who I am and where I work. And I want to point out I've provided my contact information at the bottom of this slide because I would really enjoy interacting with as many of you as possible following today's webinar. So you can learn more about SGH by visiting our website at sgh.com. And I've also included my email address and LinkedIn profile. I'd love to talk to you about our mutual interest in failure simulation or answer specific questions from today's presentation, or even discuss ways that we could collaborate or do research together. So please don't hesitate to get in touch. So this slide is just a quick graphical overview of some of the capabilities that we do here at SGH in Boston, in case anyone's interested in learning more about that. I work more in the mechanics and extreme environment simulation work, but you can see we work in a lot of different areas. Okay, so to get into the presentation for today, I'd like to begin with a little bit of background for why this is an important problem. So we'll look at the way joints perform in earthquakes and the state-of-the-art in beam column joint modeling, and then get into how I solve this problem using Diana. Reinforced concrete buildings constructed prior to the adoption of seismic design provisions embody design deficiencies which have resulted in significant economic and life losses during earthquakes. Such infrastructure exists ubiquitously throughout seismically active regions worldwide, and the large-scale risk of these deficiencies is not fully known. Beam column joints, in particular, constitute a critical component in the seismic resilience of such structures due to the fundamental role played in integrating the overall structural system in buildings. I'm showing here a reconnaissance photo from the 1999 Kocaeli earthquake in Turkey. In this photo, it's clear that joint failure was a contributing factor to the loss of vertical load carrying capacity and collapse of the structure. You can see that clearly in these two regions. The exterior corner joint failed and the building collapsed. Similar failures have been documented repeatedly during other earthquakes. I've collected just a handful here from a number of publications that I have on my hard drive. Exterior joints in gravity load design buildings typically sustain greater damage during seismic events in comparison to the interior ones. And that's something you can certainly see in these photos. You know, if you look down here, the exterior corner, here's another corner joint that failed. And the reason for this is because they're the least confined of all joints. They're only confined on two sides. They have lower axial forces due to the smaller tributary area surrounding the joint. Oftentimes there are beam eccentricities in the unsymmetric presence of the slab that cause torsion into the joint. You have biaxial bending of the column, and finally they're the furthest location from the building center of rigidity. So if the building is excited in a global torsional mode, oftentimes they have the greatest demands. But it's not only that. Barris et al. Identified 7 deficient design details common to pre-1970s gravity load design frames. And instead of going through all of these, I'd like to draw your attention to 2 of them that are important for our discussion today. The fourth being the complete lack of transverse shear reinforcement in the joint core. So notice there's no ties in the joint region. And number 5, insufficient beam bottom bar anchorage. So when we have the first load reversal and this beam is pushed upwards, and we develop a positive moment at the joint face, oftentimes we completely lose anchorage of this bottom bar, resulting in a loss of positive moment capacity along this plane. In order to better understand these deficiencies, a number of experimental studies have been conducted on non-seismically detailed joints. But typically, these joint tests were one-way planar joints without transverse beams or slab. They were typically scale models with unidirectional monotonic or cyclic loading and with quasi-static loading. So these tests provided a lot of valuable insights, but they were very simplified in comparison to the actual scenario in a building. So to address that, a number of recent studies have been completed that involved bidirectional testing of non-seismically detailed joints, including 4 members. And I'm going to talk about each of these studies as we go through the presentation today. But the important thing is that these studies resulted in damage modes that were overlooked in simplified one-way tests, most notably accelerated joint shear failure. Well, this is in fact a presentation about nonlinear FEA of such joints, and this is motivated by the challenges of full-scale experimental studies, right? They incur significant costs in terms of time and money, and these same factors make parametric investigation prohibitive. So from that perspective, nonlinear FEA provides a useful complement. We can rapidly assess various configurations and get an internal representation of the state of stress, the damage progression, and force transfer mechanisms. So before I dove into this problem, I conducted a comprehensive literature search and identified about 60 peer-reviewed journal papers where researchers used nonlinear FEA to look at the response of reinforced concrete beam column joints. And out of those 60 papers, I was able to identify 12 types of joints that had been studied. I have them labeled 1 through 12, and as you can see, next to each number, next to each of these types, I have listed the number of times that such a joint was studied in the literature. So what we can see here is that types 1 and 2 have been studied, respectively 19 and 17 times, comprise 2/3 of the database in the literature. And of the remaining that have more realistic configurations, like a slab present, most were only subjected to either monotonic or unidirectional cyclic loading. And in fact, only 1 study to date looked at the response of an exterior corner joint with non-seismic detailing. And as we've seen, these are the most vulnerable. So we need to understand the response of these types of joints better. So there's a need for numerical analysis of these types of joints. And I think it's safe to say that realistic joints have not been analyzed. And at the time of the study, it wasn't known whether nonlinear FEA was suitable to simulate these types of joints. Was it even possible? Why else? ACI 352, which is the American Concrete Institute Committee on Joints and Connections and Monolithic Concrete Structures, cites the need for further in-depth study of non-seismically detailed joints. And we're at a point now where we could actually validate such a model because of the recent experimental studies that I just presented. And there's numerous immediate applications, like parametric investigations of the factors affecting joint failure, design of innovative rehabilitation measures, planning of experiments, calibration of simplified models, and advancement towards true predictive nonlinear analysis, which I think is what we're all after. So with that in mind, this study sought to answer, can nonlinear FEA simulate the cyclic response of realistic reinforced concrete beam column joints with seismic deficiencies? And so our objectives were, first of all, to assemble a prototype model suitable for joint simulation. And this involved the lit review, experimental validation, and parameter studies, which I can only get into a little bit in today's talk. We then applied that model to analyze 4 seismically deficient exterior corner joints with increasing complexity and deficiency, including slabs, transverse beams, bidirectional lateral loading, cyclic column compression, and multiple types of seismic deficiencies. And then we'll conclude today's talk with a critical appraisal of the prototype model. So let's talk about how I went about modeling these joints. I'll make a very long story short and say that the study began with a competing nonlinear FEA code, and we turned to Diana after many months of struggling with this other software to solve this problem. So if we look back at the literature, probably at least a third of the studies on beam column joints have been completed with Diana, which was what led us to finally pursue it after we exhausted the options that we already had. So Diana, we used version 9.4.4, and I can, just to give a plug for Diana, I couldn't have been happier with this decision and how it worked out. So I think you'll pick up on that during today's presentation that I became a very big fan of Diana throughout the course of this study. So in terms of constitutive theories, I chose the total strain rotating crank model by Selby and Vecchio. So this is a rotating crank model, which means that the stress-strain relationships are evaluated in the principal directions of the strain tensor. So what that means is that crack orientations are allowed to rotate throughout the analysis based on the current state of strain. This has been, if you look back through the literature, it's been a proven approach for shear-dominated failure mechanisms. In this model, the cyclic response uses the secant stiffness for unloading and reloading, and this is very advantageous for our problem because all of the experimental results in this area exhibit a highly pinched hysteretic response, and so this helps us achieve that. And this model also allows for the evolution of the compressive strength based on a 4-parameter plasticity model. So we can see either an increase in strength due to lateral confinement or a decrease in compressive strength due to prior lateral cracking. And I've listed where some of the material properties that I used in the study came from. So in the various experiments, if they reported these values or measured them, we use those values. But otherwise, I use these common values from the literature. So I began a process of validating the model just with very simple test cases. And so I looked at, first of all, at the cyclic compression response, and I used the Thorenfeld compression hardening function, which you will find in the Diana options. And I compared it with data reported by Carson and Yersa on the left, and by Sinha, Gersel, and Tulin on the right. So these were very small prism tests of concrete and compression. And you can see that the Thorenfeld curve showed very good agreement with the backbone of the response. And again, you can see the influence of the secant unloading and reloading in the response. So there's some simplifications here, but it ended up working very well in our case. In terms of the cyclic tension response, I used the Fordic tension softening function. Again, this is available in Diana, and compared this with experimental data from Gopal Ratnam and Shah, as well as Reinhardt at Delft University. And again, you can see very good agreement with the characteristics of the experimental response, and you can see the softening in the response as we progress to greater strain levels. Let's talk about the steel model. I chose a fairly simple model, von Mises plasticity. In Diana, this is available with either isotropic, kinematic, or mixed hardening. And I chose kinematic hardening based on our experimental validation. It seems to show the best agreement with the type of data we see in tests of reinforcing bars. Note that in Diana, you can also use some more sophisticated models that account for the Bauschinger effect, like the Minigato-Pinto model or the Monti-Nudi model. So I'm showing below verification of the von Mises model with kinematic hardening with data from Ma, Bertero, and Popov. This was a study from UC Berkeley. And you can see for several different load histories, there's very good agreement between the experimental. I'll pause for a second and point out that in all the plots I showed today, the finite element result will be shown in the solid black line, and experimental results are shown in the dotted blue lines. So we can see very good agreement between the two here. In all of the studies that I'll present today, we explicitly modeled bond slip. Bond slip is a very important phenomenon in an under-reinforced scenario like a non-seismically detailed beam column joint. It tends to dominate the behavior actually when we start to have pull-out of reinforcing bars and such. Diana provides a very, very nice facility for modeling bond slip. You can use line-to-solid interface spring elements which connect the steel to the concrete, and this is really behind the scenes to the user in a way, because we don't have to. Previously, when we wanted to model something like this, we would have to actually create spring elements and manually connect the concrete nodes to the reinforcing nodes. But this new facility in Diana allows us to directly embed the reinforcing bars and automatically generate line-to-solid interface elements between them. So there's almost no reason not to include bond slip in a simulation like this now, because there's very little additional effort to providing this. So I used a nonlinear, or actually multilinear, shear slip backbone curve, which is the only input required. In addition to the, I believe on the data card, you give a specification for the interface element. And for the model that I used, for the overall model, I chose the SEBFIP Model Code 1990 guidelines for bond slip. So I'll give a very brief discussion of some of the validation I did. The experiment you see below was a study completed by Viwathan Atepa at UC Berkeley. There was a concrete block that was restrained with these straps, and there was a bar that ran through it that was subjected to cyclic action in each direction. So you can see the model of it. Here in red is the reinforcing bar that was subjected to pull out. And the first thing I'll show is that we were able to capture the typical cone formation pull-out failure that you see in a test like this. So these were some figures from the research report. You can see this cone that formed and some drawings of it. And you can see this is post-processed in FX+, a failure mechanism that bears very, very close resemblance to that. I also looked at the cyclic anchorage response of hooked bars, because this is very pertinent to our case because of having hooked bars in the joint core region. So this was a test performed by Hawkins, Lin, and Ueda, and you can see it's again a fairly simple concrete specimen with a reinforcing bar that was hooked with a 90-degree anchor, and then a cyclic displacement history was applied to the end of the bar. So again, I modeled this in Diana in FX+. You can see the embedded hooked bar here, and then sort of an isometric view so you can see the layout of reinforcing, and then the concrete mesh as well. And just to show you an idea of the force displacement response achieved in this case, there was very, very good agreement between the experimental and the numerical response. And this gave us confidence that we were headed in the right direction in terms of being able to model a beam column joint. Finally, we needed to make sure that this model was able to capture shear-dominated failure. So beam column joints fail primarily in shear. So there's no point in proceeding and analyzing one unless we have confidence that we can actually capture that type of behavior. So the cleanest way to assess this type of capability is looking at the results of so-called shear panel tests. So there's been a lot of work done by Frank Vecchio at the University of Toronto. I'm showing here a photo of their panel tester, and this setup basically allows them to apply near constant states of stress to the panel. You can see here the specimen I analyzed, some of the reinforcing characteristics. Notice that it had a shear applied in addition to an increasing compression that was simply a ratio to the magnitude of shear applied. And we're tracking this applied shear stress versus the shear deformation, the average shear deformation over the entire panel. So here's a mesh that I used to analyze this, so you can get an idea of the concrete mesh on the left as well as the reinforcing bar layout on the right. So again, all the bars are discretely modeled. You can see the boundary conditions that we use. This one was the only study that was simulated in force control, and that had to do with reproducing the boundary conditions in the test. So here is the monotonic response. The shear stress is on the vertical axis, and shear strain in the specimen is on the right. And you can see that the numerical response agrees very, very well with the experimental data. And we did further evaluations with cyclic shear panel tests, but I'm only going to present this one for now, just to give an idea that of the types of things that we can validate with Diana. Here's a look at some of the observed versus predicted crack patterns. So again, the crack patterns in Diana are a very useful tool to get an idea of the sort of qualitative response of your structure and how damage is progressing. So you can see at the end of this test, we had a number of vertical cracks, the way the photograph is oriented, and we see the same exact thing in the result in the Diana model. So to summarize, and I could go into a lot more detail about any of those points if there's any questions, but I've provided a list of the model parameters that I compiled for the analyses that we're doing. So if there's any questions about where any of that came from, we can refer back to this slide. And this process was very valuable because going through the testing each component model gave us a high level of confidence in each, so that when we start putting these things all together in a very complex simulation, that we can trust our results and not get into so-called parameter tweaking or knob turning to try to match an experimental values. Okay, let's now take that model and apply it to analyze several beam column joints. Now, before we do that, I'd like to just, to make sure we have a common vocabulary about some of the response quantities, I give a couple of illustrations. So I'll call your attention to this graphic over here on the left. This will be the majority of what we'll discuss. But you'll hear me discuss, this is representing a single hysteretic cycle in the response. The peak-to-peak stiffness of a single cycle refers to the slope of a line connecting the maximum positive drift force to the maximum negative drift level. So this is a way that we can compare the numerical response to experimental response. And then energy dissipated E sub n in a given cycle is simply the area enclosed in a single cycle. We'll discuss joint shear. Joint shear refers to the average stress or average force acting across the horizontal midplane of the joint, and then joint shear deformation refers to the average change in angle at each of the four corners of the joint. So again, you can have a look back at this if you have any questions later, but we'll be discussing these types of response. So the first experiment I looked at was the simplest. This was a one-way half-scale exterior joint. It was designed per ACI 318-63. This specimen had no joint transverse reinforcement. I'll show the reinforcing characteristics on the next slide. And this was tested at the University of Utah. So you can see in this case it was supported at the top and bottom of the column, and then the beam was cycled vertically. A couple design details I'll call your attention to. We have a splice immediately above the column, which is a non-seismic detail. And again, there's a complete lack of ties in the joint core region. Now this specimen does have fully anchored bars, beam bars in the column, but there's no transverse joint reinforcement. So here's an idea of the type of mesh that I use in this study. So everything you see in blue contained the nonlinear concrete model. The regions in the darker gray color at the column ends and the beam end were given elastic properties and somewhat higher stiffness. And this was just a method to reduce some of the stress concentrations at the load application points and distribute those forces a little more uniformly into the nonlinear regions of the model. Now, you can see again on the right the reinforcing details in the joint. So you can see that we modeled everything from the beam bars to the column bars, including all the joint ties. Now, everything in, just the ties and the stirrups in the beam. Now, all of the reinforcements, the longitudinal reinforcements have the nonlinear bond slip explicitly modeled. I didn't model bond slip with the ties because we wouldn't expect to see that. So let's look at some of the response of this for this case. So in the graph on the left, I'm showing the relationship between the beam end force, so that's the vertical force at the end of the beam, and the displacement ratio. So that is a measure of the beam end displacement divided by the beam length. So you could think of this somewhat like a lateral force drift type response. So you can see from this graph that the numerical response showed very good agreement with the experimental results. Especially in the early gauge cycles, we saw a very, very close agreement. On average, the peak force was predicted within about 5% for both positive and negative drift cycles. And on a per cycle basis, at least up to about 2%, we saw agreement less than 5% as we traced the backbone curve. If we look at the response in terms of the peak-to-peak stiffness, again, this is peak-to-peak stiffness versus the cycle number, you can see that initially the model tended to be a little bit too stiff, but after a couple cycles, we saw very, very close agreement with the degrading stiffness. So this tells us that our model is doing a very good job capturing stiffness degradation. Let's look at energy dissipation. So again, this is, well, on the left, the incremental energy dissipated versus the cycle number. We see very close agreement up until about the 20th cycle, at which point the model tends to somewhat underestimate the energy dissipation. And this is probably just a simplification from the assumed secant unloading and reloading. But there's very good agreement. You can notice that we're still, even though we're slightly underestimating, we're tracking the trend here, and by the end, we're, again, agreeing pretty well. So the cumulative energy dissipated shows very close agreement between the experimental and numerical result. In this graph, we can see the observed versus predicted final crack patterns. And again, this is a really nice tool to get a qualitative sense into how the structure is performing or failing. So you can see that at this point, remember, this is a rotating crack model, so the crack orientations will represent the current state of stress and strain in the system. So at this point, you can see this crack in the experiment has opened very widely, and you can see a band of cracks through this region that show agreement with that same behavior, along with cracking out into the beam region. Okay, the second specimen that I studied, you can see how we're gradually adding complexity. The first case was a one-way beam column joint. In this case, it's a two-way exterior corner joint with no slab. So we've now added an additional beam that's transverse to the first one. This is a 2/3 scale specimen designed per the 1955 New Zealand standard. And I'll discuss the reinforcing details on the next slide, but this was tested at the University of Canterbury in Christchurch, New Zealand. A couple comments I'll make about the specimen design here are that, first of all, this specimen contains smooth reinforcements, which is a different detail than what we've seen in any of the other cases which used deformed reinforcing bars. So we had smooth rebar. Notice again, there's no transverse reinforcement in the joint core. This is just a Y direction view, and this is an X direction view. And notice also that the beam bars are anchored with these very small 180-degree hooks, which is also a deficient detail. Now, this experiment had a very interesting setup that more closely mimicked what we might see in a real building during an earthquake, or at least some of the characteristics. There was a bidirectional cyclic load history applied to the top of the column. So I've labeled here, this would correspond to the X direction and the Y direction. And if we're looking, this graph at the right shows a plan view of the joint. The top of the column is pushed first through quadrant 1, then back through quadrant 2, then out through quadrant 3, and finally through quadrant 4. Now, this pattern was repeated at increasing drift levels, and simultaneously, the column axial force via this actuator was cycled in proportion to these loads. So when the building is out in quadrant 1, that could be thought of as like an overturning effect in this direction. The column axial force is decreased, and then when we're in quadrant 2, the column axial force increases. So this is looking at a very interesting interaction between the column axial force that's then therefore applied to the joint with the lateral force history. So I explicitly modeled these factors with the 3D load history. So the X and Y displacements were provided in displacement control, and the column axial force was cycled simultaneously using force control. Here is the finite element mesh that I used for this case. Again, this was created in FX+. Similar idea as the one before, the nonlinear concrete model applied to the majority of the specimen with stiffer elastic regions near the beam ends and the column ends. In this case, you can see on the right the reinforcing details. The column longitudinal reinforcements are shown vertically in blue, and then you can see the red longitudinal bars in the X beam, and then the green longitudinal bars in the Y beam. And again, you can see that we've modeled, in this case, the 180-degree hooks. And again, all longitudinal reinforcements are simulated with nonlinear bond slip in this case. So now we're going to take a look at the force drift response in this specimen. So I'm showing two graphs. These each correspond to the lateral load at the top versus story drift. So this is on the left, we're showing the lateral load in the X direction versus the story drift in the X direction. And on the right, we're showing the lateral load in the Y direction at the top of the column versus the displacement or drift at the top of the column in the Y direction. And if we take a step back and look at both of these graphs, we see that, again, there's a very good agreement between the predicted and observed response. You can see through the early cycles that, that the peaks are represented very closely, on average within about 5% again. And a very good agreement with the degradation of strength. It tended to be a little bit too strong in the final cycles, but very good agreement overall between these two responses. We certainly got the characteristics of the response very closely matched. So let's look at stiffness degradation and energy dissipation. So on the left, I have a plot of the peak-to-peak stiffness with increasing story drift level. Notice again, the model in the very first cycle tends to be a little bit too stiff, but as the drift levels increase, we track very, very closely with the experimentally observed stiffness degradation. And in this case, again, pretty good agreement. This is the cumulative energy dissipation. So by the end of the experiment, we had underestimated the energy by about 14%, which is, again, fairly close for this type of analysis. Let's look at how well Diana was able to predict the final crack pattern. So this is the reported damage pattern. You can see there is extensive cracking of the joint core and cracking into the beams and columns. There's also spalling in the joint core region. So this is the Diana result. And so you can see, again, a very good representation of the extent of damage. So you can see the concentration of damage in the joint core region that extends approximately to the same. If I go back and forth between these slides, you can see very close agreement between the two. And you can also see, if I draw your attention to the X direction beam, a similar sort of pattern of vertical cracks, same thing in the Y direction beam that formed in the beams. Okay, that was our second beam column joint. The third beam column joint we'll look at builds upon the last one and introduces a slab. So this is a corner beam column joint, exterior corner joint that includes the slab. It's a full-scale specimen. This was also tested at the Nice laboratory at UC Berkeley. So let's look at some of the reinforcing details in this case. This case had somewhat higher reinforcing in the beams and the columns, so better confined beams and columns. But again, if you look at the different cases, we analyzed specimen SP2, that's this one. Notice that there's, again, no reinforcement in the joint core region. Now, this one had another interesting experimental setup and loading history, and I was able to model this in Diana with no problem. I'm showing here graphs of the X-beam displacement history and the Y-beam displacement history, as well as the column compression. So in this specimen, the X-beam was cycled, then the Y-beam, then the X-beam, and the Y-beam alternatingly. Using a similar approach as the last study, the column axial force was cycled according to this equation, which was based on the current state of the shear force in each of the beams. So here's the mesh that we used in this case. This one took advantage of some of the automatic meshing capabilities in FX+, but very similar mesh to what we've seen in the previous studies today. Again, elastic regions where we applied the loads, the nonlinear model throughout all of these regions. And you can certainly start to see the complexity of the reinforcing bars. But these are very easy to simulate in Diana. I would make one copy of each of these and then copy it in each direction to fill out the reinforcing. This type of model can be generated fairly quickly with FX+. Again, you can see that we have anchored beam bars in the joint core, but there's a complete lack of any transverse reinforcement in that region. So here is the force displacement response at the end of each beam. So this is the x direction beam. This is the force at the end of the beam versus the x beam displacement. And then on the right, we see the beam and force on the y direction beam versus the y beam displacement. So this should say y. And again, notice very good agreement overall with the characteristics of the experimental response. The peak capacity in each direction was predicted within 4%, and very good agreement in later cycles. You can see that we achieved a highly pinched response, which is what the experiment indicated, and good agreement. In terms of the stiffness degradation, which I have shown on the left, you can see the peak-to-peak stiffness with increasing beam displacement ratio. Again, very close agreement. So the model under increasing cycles can show can predict the way the stiffness of the system decreases. And then cumulative energy dissipation in this one, we can see that we somewhat underestimated the energy dissipation by about 20% by the end of the simulation. I'll look at a couple crack patterns here that again give us a sort of a visual sense into what's happening in the joint core. The photo I show on the left is at this point in the displacement history. So the beam is being pushed up, and this is right at the point where the joint starts to really show damage for negative drifts. And you can see the formation of two very large cracks. There's one that goes up through this area and then another through here. And notice that our rotating crack model, if we view the crack pattern, we can see a very good sense of the diagonal cracking in the joint core, which we expect. Also a concentration of damage at the joint face, which we can see in this region in the experiment. You can see this crack coming through here, and you can see another diagonal crack like this. The picture on the left shows the following cycle when the beam is pushed downward. And you can see that now a very large crack has formed somewhat perpendicular to the ones we just saw. So this is a very typical joint shear failure we see in a beam column joint with the X pattern cracking of the joint core. And at this point we can see now that these cracks have realigned in this direction to give us a sense of the direction of cracking in the current state. The final experiment we'll look at today was simulated at Georgia Tech by a friend of mine, Murat Ngendenez, who also works at SGH in Boston with me. This was a two-way corner joint with slabs, so it's very similar to the last specimen that we looked at. It's a full-scale specimen, and it's designed based on ACI 318-63. This one had a constant axial load history and a bidirectional cyclic loading history that looked like the following. So you can see here that there's an actuator attached to the end of each of the beams. The top of the column is penned. And there's a single cycle, or in the experiment, 3 cycles applied to the end of this beam, 3 cycles applied to the end here. And then after that, each of the beam ends were cycled simultaneously. So this simulates what we might think of as a worst-case scenario for a 45-degree loading of the building. Let's look at the reinforcing details. This was the most efficient joint that I looked at during this study. It has all 7 details that Barris et al. Identified, which I showed in an earlier slide, and I'll point out some of these now. First of all, there's the column splice immediately above the joint core that is not only located at a problematic place, but is inadequately confined. Notice in general that the column and the beam do not have much confinement. The beam top bars are anchored in the core with 90-degree hooks, but notice the beam bottom bars travel through the beam into the joint, and there's only a 6-inch or 150 millimeter embedment. So you can imagine what happens when you push up on this beam, that it doesn't take much to lose anchorage of this bottom bar. The final thing I'll point out is that there was no confinement of the joint region. So it's a very deficient joint from a seismic perspective. So here's an idea of the mesh that I created for this specimen. You can see there's two colors of blue because there were two different concrete pours that were used to create this. There was actually a construction joint in the experiment between these two regions as well. So you can see that again, the location of the actuators and the supports are in the dark gray colors, and then we have the nonlinear properties everywhere else. This is an idea into the reinforcing bar mesh for this specimen. And so again, I've modeled the reinforcing bars with very high fidelity. So I've captured things like the splice region you can see here. The column bars are doubled, so these are bundled bars. You can see that the top bars in the Y-beam, the green ones, as well as the top bars in the red from the X-beam are anchored with the 90-degree hooks, but the bottom bars just have a straight embedment. So I've taken care to model all the details. Again, this is a fairly straightforward model to set up in Diana. We can just, again, model one of each of these and then just copy it into place, and then just select and notify Diana that these are embedded reinforcements, and Diana will take care of the rest. So let's look at the force displacement response for this specimen. So again, we're going to look at the, in this case, the force at the end of the beam. So this is for the X direction shown on the left. So we have force at the end of the beam versus the beam displacement ratio again. And then on the right, we have the force at the beam end of the Y direction beam plotted versus the displacement at the end of that beam. So if we take a look at these graphs, we can again see that there's very good agreement between the Diana model and the experiment. The peak force in each case tended to be slightly over-predicted by about 6%. But notice, if we compare them on a per-cycle basis, so if we look at the prediction during every cycle, that the prediction on average is within less than 2% with what was experimentally observed. Now, one thing you'll notice in this experiment is that I've only simulated a subset of the cycles that were tested experimentally, and this was due to computational cost. The solution time was too long to simulate all the cycles, but this shows that even in a case like this with a model like the one we're using in Diana, we can get a fairly good representation of the response while only simulating a subset of what was actually conducted in the experiment. In terms of stiffness degradation, you can see on the left, our peak-to-peak stiffness was initially too stiff. This was something we've seen in all the specimens. But again, after one or two cycles were completed, we saw very, very good agreement on peak-to-peak stiffness. And this specimen showed the best agreement in terms of cumulative energy dissipated. So the plot on the right is the cumulative energy versus the cycle number. And you can see that for the first 3 cycles, that experimental and numerical response are almost indistinguishable until we get to the final cycle and we see a little bit of deviation. But very, very good representation of the cumulative energy dissipation. Now, the joint shear response is an interesting quantity. I'd like to actually, before I show this, I'll back up to this figure for 1 second. So one of the things we noticed in this experiment is that the negative moment capacity, the negative drift capacity tends to be much higher than the positive drift capacity. We see that in both directions. Well, the reason for that is because of the difference in the anchorage characteristics of the bars. If I push down on this beam, the beam bars are well anchored in the joint, so we have a fairly high moment capacity at the column. Versus if we push up on this beam, these bottom bars tend to pull out, so we have a very low moment capacity at the joint face. Well, this is seen in the force displacement response. So if we look, when we're pushing down on the beam, you can see we have a higher capacity, almost 30 kilonewtons versus, well, actually our datum is about plus 20. So you can see if we're thinking of this as the datum, that we have a difference of about 48, 50 kilonewtons in this direction versus about 30 in this direction. See the same thing over here much higher moment capacity in this direction versus this. That's also seen in the joint shear response. So again, this is looking at the plot, the joint shear, which is the average shear stress across a horizontal midplane in the joint region versus the shear deformation in the joint. So you can see that pushing downward, we have a very high joint shear capacity. So we can develop high lateral forces in the joint region due to the anchorage of the beam top bars. Versus when we push up on the beam, you can see for both the X direction and the Y direction that, that we have much lower joint shear capacity in both directions. Now this is important because it indicates that our model is doing a good job capturing the lack of anchorage of the beam bottom bars. So the bond slip simulation of the beam bars appears to be working very well in terms of capturing the stress state in the joint region. Now, again, notice we've only simulated 1 out of every 3 cycles, so the numerical results don't progress out quite to as large of shear strains. But if you compare it on a per cycle basis, you can see that there's very good agreement with the joint shear stress strain response. I'd like to point out the final damage contour in this case. So because this joint was so poorly detailed, it doesn't exhibit the typical X-shaped cracking that we expect to see in beam column joints. You can see that when the beam was pushed upwards, that the actual first crack that we saw was at the joint face. This is at the location. Recall that we have beam bottom bars that come into the joint like this, embedded about 6 inches. So those bars are the first to lose anchorage, and as we push up, instead of forming a series of X cracks, we actually form a crack at the joint face that moves upward and then progresses through the joint up into the column. And you can see a similar trend qualitatively in the crack pattern here, a sense of cracking that sort of progresses in these 2 directions. So again, nice tool to visualize how the joint is performing. Well, I'd like to conclude by sort of summarizing how the model did, and then I'll discuss some outcomes and recommendations. So I've compiled the various response metrics over the 4 beam column joints that I studied. So these are the 4 specimens. So the first is, again, the one-way joint, and then the joint with transverse beams and no slab, and then finally the 2 specimens with transverse beams and slab. And now you'll notice, I'll call your attention to the mean values. So as we go across, F refers to the peak force. So on average, we were able to predict the peak force within about 3%. If we considered, if we wanted to know what was the peak force in any given cycle, we were able to do that within about 10%. That's because the model tended to, in some cases, be a little too strong in the post-peak cycles. But again, this is very good agreement overall. In terms of peak-to-peak stiffness, the model tended to be slightly too stiff, and this metric is really dominated by the initial stiffness. But once we've accumulated a very minimal amount of damage, we see very good agreement with peak-to-peak stiffness. And we tend to slightly underestimate the cumulative energy dissipated in the system. And then finally, the joint shear response shows very good agreement, less than 5% difference with the experimental values. I didn't show this result for all the cases that I presented today, but this was compiled for the ones listed above. And this is important because this is really one of the key design metrics that we use for beam column joint performance. So it's very encouraging that we can have confidence that this type of model can capture the joint shear performance. So what were some outcomes of this study? The validated model was highly effective in simulating the response of 3D beam column joints with seismically deficient detailing. To my knowledge, this was one of the first known successful studies using nonlinear FEA of non-seismically detailed reinforced concrete exterior corner joints, including a slab. So I think this is an important contribution and opens up a lot of doors for further for either further research or for application of tools like this in companies like Simpson Gumpertz Heger or wherever where we can actually use a tool like this to characterize the response of an existing joint and then use that to develop simplified models or do various performance-based evaluations. Okay, the third item. I would highly recommend the systematic experimental validation of all component models as being very crucial to gaining confidence in the model, to being confident that you are using it correctly. One of the temptations we all face is when we have a complex problem is to immediately start putting all the pieces together and try to model the final behavior. But unless we've really studied each component, it's very difficult to know when results don't match what is the source of the problem. And so by going through the systematic process, I was able to analyze the beam column joints that I predicted without any parameter tweaking. So the previous slide where I summarized all the model parameters stayed constant throughout all the simulations, and we can see that that's an important step towards predictive analysis, right? We don't want to just tune a model to a specific experiment, but we want to be able to predict how a system will respond blindly. And I saw that with Diana this is possible. I found that Diana was a very capable tool for nonlinear analysis of concrete behavior and highly recommend its use for other researchers or consultants attempting to simulate failure processes and brittle materials. I mentioned that I began my study using a competing nonlinear FEA code that was already available to me in-house, and that was finally abandoned because of convergence difficulties. But when I made the move to using Diana, I encountered no convergence difficulties throughout the course of this study, at least none that I could not easily diagnose and remedy. So this is almost unheard of, I think, in terms of solving as unstable a problem as the one that I was looking at. So I think you'll be very, very pleased using Diana for a nonlinear simulation like this where convergence is difficult. Okay, what else? The rotating spear crack model, I believe, is very appropriate for prediction of shear-dominated failure mechanisms. Again, this just confirms what we've seen throughout a couple decades of literature that recommends rotating crack models for shear-dominated failures. The cyclic formulation of this model is particularly helpful when trying to capture a hysteretic response that's highly pinched. So this is another difficulty that that you will run into with other softwares that Diana does very well. A lot of other softwares tend to highly overestimate the energy dissipation, and Diana handles this very well. So the final specimen that I looked at, the Ngandena's simulation, accurately produced the sudden loss of positive moment capacity and joint shear strength under upward beam loading, which confirmed the model's ability to capture pull-out failure. Again, this was a very key finding that opens up a lot of doors for simulating non-seismically detailed situations like this. So we can capture the pull-out failure, then we can have confidence that we're really analyzing a real beam column joint, because this is a very common failure mechanism and what we typically see in that type of simulation. And then a couple other tips. One of the things that I was interested to find was that the model, correct simulation of the column axial force was critical for accurate strength prediction. So it's very important in the cases that I showed to get the column axial force right, especially when it was under cyclic load. This highlights the influence of confinement. So as I mentioned before, the model in Diana can account for the influence of confinement on the strength of concrete. So the fact that the model is sensitive to this, but when I modeled the column axial force correctly, the capacity was very close, again, was a very encouraging sign that we have a very capable model, and that is being used appropriately in this case, right? So if the column axial force is decreasing, right, we would expect that its shear capacity is going to decrease because it's not as well confined, and we saw that effect very, very closely captured. And for a simulation like this, the final sort of tip that I would give is that these results can be very sensitive to the support conditions and partial restraint. And I didn't get into this in the presentation, but there were cases where it was very important to model the relative stiffness of the loading apparatus or various support conditions to accurately transfer appropriate forces into the system. So all in all, I couldn't have been more pleased with the outcome of using Diana in this study, and highly, highly recommend it. So this will conclude my presentation today. Again, I want to thank you so much for attending, and I've included my email address here again, and like I said, I highly encourage you to please get in touch with me. I'd love to meet anyone who is a part of the webinar today. I'd love to talk about nonlinear concrete modeling, or even SGH, the kind of work that we do here. Love to discuss ways that we could collaborate or get to know each other. So at this point, I will conclude the presentation. Thank you again for your attention, and if you have any questions, I'd be very happy to answer those at this time. Thank you.
Thank you, Ben. It was very informative presentation, and highlighting all these complex effects and factors or characteristics and the effect of them in cyclic behavior of the joints. It was very impressive. So already we received a couple of questions. I would like to share them with you. So based on type of questions, feel free, if they are quite generic, you can use microphone so I do not mute you. Or you can type them back, and we can also get back to the questions by email if you need additional information or detailed parameters. So I go through them and share them with you. You may find them in the chat box then.
Okay, I'm seeing some of the questions now, so I will I'll cycle through some of these and try to answer them overall. So first question, do you have a sense for how much bond slip contributed to the overall behavior in these sufficient joints? Were any models run with perfect bond as a comparison? And the answer to that is yes. I did a number of parameter studies, and initially I was curious to find out whether it would be possible just to model these with a simpler model without bond. And the things that I found were that not including nonlinear bond slip resulted in models that were much too stiff, especially in the early cycles. So they were too stiff and too strong. So I think for a deficient joint like this, it's almost required that you would use bond slip. Let's see. Okay, next question. Do you try to increase the column axial load in the numerical models? So I tried as closely as I could mimic it. I attempted to model exactly what was present in the experiment. So in two of the experiments, the column axial load was applied cyclically according to a function, and I explicitly modeled that so that it was exactly matched what was applied. In two of the experiments, the column axial force was effectively held quote-unquote constant, which means that the column axial force was applied via a number of steel rods and then was held constant. But the steel rods actually have a non-negligible relative stiffness in comparison to the concrete specimen. So for instance, if you have a column, one of these joints with column axial force plugged with rods, and you push the beam upward, well, that upward force is going to actually extend the column rods and increase the column axial force, versus if you push down on the beam, it'll actually relieve some of the tension in the rods and decrease. So in those cases, what I actually did was I modeled the column axial force using an elastic spring, which had the same stiffness as the rods, and then I used a support displacement to enforce that condition. So this very closely mimicked the idea of the somewhat varying column axial force. But I tried very hard to make sure that it closely matched the response, or the exhibited column axial force. So one of the questions was, how sensitive was the analysis to the mesh step? Did you have any specific criteria for selecting the mesh step? And what I can say about this was that this was really just a process of trial and error. So for especially the earlier studies, I did some parameter studies where I attempted a much finer step size in the solution control versus broader ones. And so what I did was I would systematically vary it, and I would track what was the influence in the response. And so I performed, I guess we would say, more of a qualitative optimization of that parameter by looking at that, because we were already pushing the limits of the size of the models that we could practically solve. So we wanted to have that step size as large as possible without really sacrificing any quality. So it would always be better to have a smaller step size, I think, for this kind of analysis. But it's one of those cases where I think at the end of the day you have to do the best you can, and that was what we did. So I recommend that type of study, right? Try several different levels and plot them and compare the results. Look at stresses and strains. And try to make sure that the results make sense and that you have comparable results before going to too large of a step size. Okay, here's a question. Can you estimate the cost savings between using FEA simulation and physical experiments? I think that the main thing that I can discuss there is in terms of time. So I think for a graduate student, doing this the first time, it can take a while to learn the software and use a tool like this to assess the response of a joint like this. But I could say that after learning how to use this tool, this type model can be built and analyzed in the order of a week or two of full-time effort. And so this is the kind of thing we do here at Simpson Gumpertz and Heger. We need results quickly. So we will spend the time developing expertise in a tool like this, so that when we have a building we're evaluating that has a component, we can have confidence that we can evaluate it quickly without having to contract a laboratory to do the work or something like that. So I think it's very competitive from a cost standpoint. And the nice thing about the FEA is that once we've built the model, we can easily vary these different parameters. Like for instance, if we are designing an FRP retrofit, we can analyze a joint using a tool like this, and then we can test 5 different retrofit or rehabilitation measures that we could never do in the lab. So I think it's highly cost effective with respect to experiments, but the catch is that, as I'm sure you know, we have to have valid experimental data for a similar problem that we can use to validate our model, so that we can be confident that our results make sense, right? We know with FEA we have to be very skeptical of our results and be very critical of the numbers that we produce. So I'm not an experimentalist, so I can't necessarily comment on the exact same cost. But I think it's I think it's much less expensive, at least in terms of time, and therefore I think it's highly recommended. Okay, here's a good question. Doesn't not modeling bond slip in stirrup prevent the possibility of having opening of stirrups that could induce further buckling? And that's absolutely true. So that's a simplification in the studies that we did. I don't think that any of the beam column joints that I simulated were really dominated by the type of failure like what you're referring to. I mean, they were really dominated by failure within the joint core and at the interface of the joint to the beam and to the columns. So I think in general that's a very good point. It wouldn't have been much additional effort to do that, but that was a simplification that I chose that I don't think had much influence in this case. But certainly I wouldn't have a problem with doing that in the future. Okay, another good question. The model was calibrated using quasi-static tests that do not incorporate strain rate effects. How would the model perform under dynamic effects? Well, this is an interesting question, and something that I'm very eager to look at. So we know that reinforced concrete, at least under seismic type loading, like a realistic ground motion, that strain rate effects don't play a significant don't have significant influence in the response to the structure. So I don't think that that it would make a big difference if we're doing a seismic evaluation. Now, certainly, if we're going to model some type of impact or blast type loading, then the ability to define the constitutive theory in terms of rate effects is going to be an important consideration. But I think the main thing that would limit the performance of the model in terms of a dynamic analysis is just going to be the computation time. But I would be very interested to explore that, and that's something that I wanted to do, but just wasn't able to in the context of the current study. Okay, here's another question. So with respect to the Park and Mosalon study, as well as, and I think this applies to the Inga-Dennis situation as well, why were less cycles performed? Well, if you notice, with the first two specimens, the one-way joint and then the Augusel specimen, which was the two-way joint without slab, I applied all of the experimentally conducted cycles to the specimen. With the Park and Inga-Dennis specimen, we had not only a bidirectional load history, so you could think of it as the simulation was already twice as long as the prior because we were loading in both directions, but also the influence of the slab introduced quite a few more elements. So that decision was driven by nothing other than the computation time and the resources. I was performing these studies on a local desktop with a solid-state drive, and so I didn't really have access to high-performance, computing resources. So that was a case where I was just doing the best I could with the resources that I had. But I think that I would expect that, certainly these experiments, the load history is important, and accumulated damage from these, especially maybe repeated early cycles, has a large influence. So we saw pretty good agreement without that, but I would expect that to improve with more cycles. So certainly I would recommend, if there's any way possible, simulate all the cycles. In everything, try to match the experiment as closely as possible with the resources that you have. Okay, here's a question. I think this is referring to how the steel rebar are simulated. So yeah, so the steel reinforcements, I'll just kind of review some of how that was constructed. So the steel reinforcements can be embedded as either truss or beam elements within the concrete. And so the steel reinforcing bar itself had a von Mises plasticity model with kinematic hardening. And then in between the steel reinforcing bar with the plasticity model and the concrete model with the rotating crack model were interface elements that allowed a nonlinear shear stress slip relation in between the two. So I think so all the components were modeled with nonlinear behavior so that we could have cracking of the concrete, slip between the bars, as well as yielding of the reinforcements.
Well, Ben, thank you very much. I think there are some questions that we can always get back to them by email and say if there are some additional technical notes are required, we can attach them. But maybe we could kind of wrap it up at this moment and leave the discussion open via email if you're agreeing with that. Is that okay with you?
Yeah, that sounds great. Thanks again, Maz.
Thank you, Ben. It's really appreciated, and I hope, as I really learned a lot, all the audience and attendees enjoyed the session. And we leave this discussion open by email. You can either directly email to me or Ben, and we would be more than happy to answer all your questions. So wish you a pleasant time, and once again, thank you, Ben.
Thanks very much.
Bye-bye.
Bye-bye.